Hi, I'm Avik. I have been teaching physics on NEET and JEE for more than 5 years. I have been also ex-AGD at Career Point, and I myself am from NIT Warangal. Acha, okay, so enough about my credentials. What are we going to do today? So today we are going to study something about rolling motion that usually isn't performed in the books. That means that usually are explained in a little bit untidy manner in the books. Okay. So what my request are is just follow through the lectures. And this 20 minutes will give you the best understanding of the rolling motion, the concept of rolling motion that's out there. Okay. And after understanding the concept, there are certain questions that I'll be providing in the link, and do follow the questions. Okay. So after you have completed both the tasks, I guarantee you there's going to be no one that can challenge you in the concept of rolling motion. Okay. So is the deal fair enough? So let's start with the concept of rolling motion. Rolling motion. Now the first thing, okay, the first intuition. Instead of getting with the first intuition, let's just do or what everyone's or let's just start at the base where everyone starts. Okay. So a wheel is rolling on the surface of a road. Okay. This is the wheel, and this wheel is rolling on the surface of the road. So this wheel is going with some velocity. Okay. The velocity of the wheel is nothing but the velocity of the center of the wheel. Okay. So if this is the center of the wheel, whenever I talk about velocity, I'm talking about this part or the motion of this part. Okay. And this wheel is also rotating with angular velocity omega. Now I can divide this motion or rolling motion of the wheel into two components. One is pure rotational component. That means the wheel is only rotating with angular velocity omega. I won't see any other motion apart from the rolling motion, apart from the rotational motion. And the second one is purely translational motion. Okay. So these two motion will combine the rolling motion of the wheel. Now the first kind of question that we'll ask is, what is the velocity at this point, or what is the velocity at this point, or what is the velocity at this point, or what is the velocity at this point? The velocity at this point of the wheel will be nothing but a combination of velocity of this point plus the velocity at this point. Okay. Now due to pure rotation, what is the velocity at this point? It is nothing but omega in this direction, isn't it? And what is the velocity at this point due to pure translation? It is nothing but v at this point. So the combined velocity would be nothing but the total velocity at this point would be nothing but v plus omega. Okay, where r is the radius of the wheel. Fair enough. Now if someone asks what is the velocity at this point, or at this point, or at this point, okay, this point, and this point. So velocity at this point is nothing but omega in downward direction, isn't it? So this will go in downward direction, and velocity at this point due to translation would be in this direction. So the combined velocity of this point would be nothing but v plus omega, isn't it? So this would be a vector quantity, and the resultant vector would be in this direction. Understood? Okay. So if I have to point out, this is nothing but omega r, this is nothing but v, omega r, omega r, and omega r. So you get the idea. The velocity at each point is nothing but a combination of rotational velocity and translational velocity. Rotational component of velocity and translational component of velocity. That's the basic start, or that's the basic presumption of rolling motion. Okay. Now there are few things that you need to learn. The first thing is the condition for rolling motion. When is rolling motion possible? When is rolling motion not possible? See, one of the fundamental things that you need to put in mind friction force is necessary for rolling. That means without friction, no amount of rolling can take place. Okay, friction force is necessary for rolling. Without friction, you can't have any rolling. Friction force is necessary for rolling. Okay, without friction force, there cannot be any type of rolling. Now, since we have introduced the concept of friction, there has to be a direction of friction. So my next kind of discussion would be, or topic of discussion would be, direction of rolling force. Okay, so direction of rolling. Direction of rolling. Not direction of rolling. I did a little bit of that kind of here. Direction of friction force in rolling motion. Friction force in rolling motion. Okay. The first thing you need to understand, see, whenever I'm giving a rolling motion, okay, suppose this body is rolling on a surface. This body is rolling on this surface, V omega. Okay, there is some relation between V and omega. I'll get to that later. But to find out the direction of rolling, you first need to see this surface. Okay, this surface. Okay, I need to find out in which direction does this surface tends to slip. Okay, so if the wheel, if this wheel tends to go in this direction or tends to slip in this direction, that means the friction force would be in this direction. Okay, if the wheel, if the base tends to slip in this direction, the friction force would be in opposite direction. Okay, so my primary question is, how do I find out in which direction is the wheel tending to slip? See, imagine if there was no friction force. Okay, if there was no friction force out here, mu is equals to 0. How would this wheel, or how would this wheel move without friction? Okay, you have to assume how would this wheel move without friction, and then imagine the surface, in which direction is the surface trying to go. Okay, and after that friction force will be applied in the opposite direction. Okay, let's see some example best. Okay, so suppose there is a wheel. Okay, there is no external force out here, rolling like that. Okay, omega. So if there was no friction force out here, see, if there was no friction force out here, this part would try to slide out here. Okay, this part would go out here without any slipping, isn't it? So the direction of friction force would be in this direction in this case. Okay, fair enough. So show us some more examples. Yes, I'm going to do that. Okay, just keep a little bit of patience. Friction force. Now what happens if I take the wheel, okay, and let's say I apply a force F out here. Okay, in which direction would the friction force be applied? If I apply a force out here, okay, so this surface would try to rotate in clockwise direction, isn't it, in this direction. So if this tries to rotate in clockwise direction, this surface is trying to go in backward direction. That means this surface is trying to go in this direction. So friction force out here would be in opposite direction, or this direction. Okay, so this is the direction of friction force. Again, suppose I shift this force somewhere down out here. Same concept. Okay, this is trying to rotate in clockwise direction, and this surface is trying to go backward. Friction force would happen forward. Okay, friction force would be applied in forward direction. Fair enough. Now what happens if I apply my force out here below the center? Okay, see out here, if I apply the force below the center, what would happen? This wheel would try to rotate in anti-clockwise direction, try to rotate in this direction. So this surface would try to slide in this direction, and therefore the direction of friction force would be nothing but in this direction. Understood? Let me make this neat and clean. Okay. Now let's take a little bit of more complicated examples. Not complicated examples. Let's see. Okay. So this will, if I apply a force at the center, okay, when I apply a force at the center, what is happening is this surface is trying to slip in this direction without any rolling motion, so the friction force would be in opposite direction. Understood? So the direction of friction force would be in this direction. This is the direction of friction force. Fair enough. Now my question is, what would be the direction of friction force in this case? Suppose there is an inclined plane, okay, and there is a wheel out here. So in this case, mg sin theta is acting in this direction, isn't it? This is the angle theta. Now see, if there was no friction force, the surface would try to slip in this direction, so friction force, see, the surface would try to slip in this direction, so friction force would be in this direction. Fair enough. Let's complicate the example a bit. Yeah. So this is an inclined plane and this is a wheel, and in this wheel there is a wrapped coil rope. Okay, this rope is holding the wheel, this rope out here is holding the wheel, and this rope is coiled in the wheel, and this surface has friction. Okay, now in which direction is the friction force? See, if there was no, see, find out the direction of friction force. First you need to assume there is no friction force, and find out the direction in which this surface is going to slip. Okay, and then apply the friction force in opposite direction. Understood? So if there was no friction in this surface, the wheel is attached to rope at this point, isn't it? Through this one. See, mg sin theta is acting in this direction, so the wheel will try to rotate in anti-clockwise direction, isn't it? So this surface is trying to slip in this direction, isn't it? So the friction force out here would be nothing but in this direction. Understood? Now let's take an example of cycle. Suppose this is a cycle, okay, and you're paddling in it. Okay. And the question is asking, find out the friction force in back wheel and front wheel. That means find out the direction of friction force in this wheel and find out the direction of friction force in this wheel. See, when you apply the pedal, what happens is this wheel tries to rotate in this direction. Imagine this surface to be made of ice. Okay, there is no friction force out here. Then when I apply the wheel, what happens is this wheel try to rotate in this direction. So this wheel, this surface would try to go in this direction. So direction of friction force in the back wheel will be in forward direction. Okay, and now imagine this surface or this wheel has friction force right now in this direction, and the cycle is going forward. Okay, now what is the direction of friction force in this wheel? Okay, see, when this cycle goes forward, see, there is no pedal power given to this wheel. Okay, so this wheel will only go forward because the spoke is connected out here at the center of the wheel, and this spoke will push the wheel in forward direction. So this would be the case of this problem. Understood? So without friction force, this wheel would try to move linearly without any rotation, isn't it? And this surface would try to go in forward direction, so that type of friction force would be in backward direction. So for a cycle, okay, the back wheel experiences friction force in forward direction and the front wheel experiences friction force in backward direction. So by now you have fairly a good understanding of the direction of friction force in case of rolling motion. Okay. Now the more prominent question. Sir, I have understood the direction of friction force. Okay. So what is the value of friction force? Okay. Value of friction force. So values of friction force in values of friction force in rolling motion. In rolling motion. Okay. So to find out the values of friction force in rolling motion, you first have to determine what kind of rolling motion is it. Okay. Is it a case of pure rolling? Or is it a case of impure rolling? What are these pure rolling and impure rolling? What are these? Okay. See, pure rolling is the case when this surface. Pure rolling is the case when this surface does not slip over the surface. See, what I was trying to do in the direction of friction force while doing the direction of, I was assuming that there was no friction out here, and then I was finding out the sense of rotation, and then friction force was applied in the opposite direction to the sense of wind. Okay. However, in case of finding the magnitude of friction force, you need to first see this surface. This surface is slipping or not. Okay. If this surface is slipping, okay, then that is a case of pure rolling. Sorry, impure rolling. Okay. That is a case of this impure rolling. And if this surface is not slipping, that is a case of pure rolling. Okay. Now if I look little bit behind, that means, what did I say? If this surface is actually slipping, that means that is a case of impure rolling. And if this surface is not slipping over this surface, that is a case of pure rolling. So in case of pure rolling, this surface is not slipping. That means the velocity at this point in the wheel is equals to 0. So how do I get the velocity at this point is equals to 0? Velocity at this point is nothing but omega r in this direction plus v in this direction, isn't it? So v minus omega r is equals to 0. So the condition for pure rolling is nothing but v minus omega r is equals to 0. Or if I write it neatly, I can say that v is equals to omega into r, or velocity of center of wheel is equals to angular velocity into r. And in case of impure rolling, v is not equals to omega r. Okay, that means sliding and rolling or rotational motion, sliding motion and rotational motion are happening independently. Okay. Now, in case of pure rolling, static friction acts. Static friction force acts. Okay. And in case of impure rolling, dynamic friction force acts. Dynamic friction force. Okay. So by now you get the idea that if v is not equals to omega r, okay, then friction force I can directly write as mu into n, and in most of the cases n is mg out n. Okay, most of the cases, not all the cases, but most of the cases. For pure rolling, however, you cannot find the value of static friction force directly by any formula. Okay, you have to use your equation. That means there will be various equation outside. Various equation in the problem. By solving those equation, you need to find out the value of static friction force. Okay, because by definition, the values of static friction force is nothing but minimum value of unbalanced force and mu n. That means friction force will have the minimum of unbalanced force or mu into n. Okay, and you know some concept of static friction. Okay, that means if the block is trying to move, the value of friction force is unbalanced force or mu into n, whichever has lower value, isn't it? You learned that in chapter of friction. Okay. Now let's see some examples of the thing that we have learned. Okay. So let me open up my book. Let's take this example. Okay. Let's draw this example out here. So this is a question from HCV. and the later part of the HCB are a little bit of difficult. So there is don't presume this question to be difficult. Okay, just see what I'm doing out here. So suppose this case, what the question is basically saying. So there is this wheel. Okay, this wheel is there. This wheel is there. Okay, and initially it was given an angular velocity in this direction and a linear velocity in this direction. That means initially this surface was slipping because V is not equals to omega r. See, the sense V is equals to omega r, V has to be in this direction and omega r has to accompany the V in this direction. Okay, so initial cases, this surface was slipping. So the friction force is acting, the direction of friction force is nothing but, since the surface is slipping in this direction, friction force is acting in this direction. And this friction force is causing two things. It is decreasing the velocity and it is decreasing this angular velocity in this direction. So after a certain while, what will happen? After a certain while, this body would become zero velocity or zero angular velocity, okay, and some reduced velocity v. Okay, so initially, let me draw out the diagram. Initially, it was given angular velocity omega. Okay, omega is equals to v by r, and linear velocity v. And this is a case of impure rolling, the direction of friction force would be mu into n or mu mg. Okay, after a certain while, what would happen? The angular velocity would be zero. Okay, and what is causing this angular velocity to be zero? The friction force, the torque caused by friction force, and this velocity would reduce to be v1, some velocity v1. Okay, now if I ask, what is the direction of friction force out here? Okay, what is the direction of friction force out here? See, if I draw this as a surface, okay, v1, this surface is also trying to slip in this direction. So even now the direction of friction force would be in this direction. Okay, and the value of friction force is nothing but mu into n, because this surface is trying to slip. Okay, so in case of slipping, the values of friction force is nothing but mu into n, or the dynamic friction gets applied. Friction force or mu into n. Okay, let's write this as mu into n. And again, the job of this friction force is nothing but, the job of this friction force, where is it? Is to nothing but, see, now this torque caused by this friction force would increase the angular velocity in this direction, but the force due to this friction force would decrease the velocity in this direction, because now if I do linear analysis, the acceleration would be in this direction, but the angular acceleration would be in this direction. In first case, the angular acceleration also is in this direction and the linear acceleration was in this direction. And the linear acceleration is caused due to this force mu n. The angular acceleration is caused, the torque caused by this force mu n. Understood? In the second case also, the torque would be in this direction and the angular acceleration would be in, linear acceleration would be in this direction. But in the second case, the torque is actually speeding up the wheel in this direction. Okay, and this friction force is actually reducing this velocity in this direction because the acceleration is in this direction. Understood? So this is by yes. Okay. So okay, and my question now out here is, till what condition would this friction force act? Till it obtains the condition of pure rolling motion. Till it obtains the condition of pure rolling motion. Okay, that means what is the crux of this, or what is the conclusion of this is, in case of pure rolling, okay, in case of impure rolling, friction force, okay, so in case of pure rolling, friction force will only act till the condition of pure rolling is achieved. That means the value of mu n, or the value of dynamic friction, will only be there till the value of till the thing, objective of pure rolling is obtained. Okay, in case of pure rolling, okay, not in case of pure rolling, in case of rolling motion, dynamic friction force. Dynamic friction force means mu into L. Dynamic friction force only acts till the condition of pure rolling is achieved. Understood this one? So you might ask, sir, what happens after pure rolling is achieved? Okay, so out here the wheel goes to the motion of pure rolling. Okay, after this what happens? Does the friction force disappear? No, this friction force still exists. Okay, and this would be a case of rolling motion, pure rolling motion, where V is equals to omega. That means it would be some V2 and it let this omega be some omega 2. Out here, after the condition of pure rolling has been achieved, V2 is equals to omega 2 into R. But right now, the value of friction force won't be anymore mu into N. That means this friction force, okay, has demoted itself from mu N to some value of static friction force. And the value of static friction force cannot be found out directly. You have to find out the value of unbalanced forces. Understood? And this static friction force in some books is written as rolling friction. Okay, so there exists nothing as rolling friction. The static friction in case of pure rolling is bundled as rolling friction in some books. Okay, so that concept is a little bit wrong. Understood? Now one more thing, sir, what would happen if I leave this wheel in this condition? Okay, so will it stop ultimately, or it will keep rolling, or what would happen? Okay, see, in Newton's first law of motion, you learn that a body with velocity v keeps on moving with velocity v until and unless an external force is acting on it. Okay, so this body with velocity v2 and omega 2, there is a friction force acting on it. So this is supposed to stop, or what is supposed to happen? See, after the condition of pure rolling has been achieved, okay, the friction force is acting, but the work done by friction force is zero. Okay, so remember this one. In case of pure rolling motion, friction force is there, static friction force is there, but the work done by static friction in case of pure rolling motion is zero. In case of pure rolling means V is equals to omega. V is equals to omega. Static friction exists. Static friction exists. But the work done by static friction, is zero. Is zero. So since no force is doing any work out here, so if I leave it as it is, so this motion after achieving a condition of pure rolling motion would continue this forever. Okay, that means this body would roll indefinitely. Okay, V2 in this direction, omega into this direction. There is no one to decrease this V2, no one to decrease this omega 2. You might say, sir, friction force is acting on V2. No, obviously friction force is acting on V2, but the is zero on this body. Okay, so no work is done by this friction force. So the value of V2 and omega 2 won't change. Okay, sir, how do I distribute this work, or how do I relate this work done by friction force? This and sublet of this topic of rolling motion. Okay, so let's hold this question for a minute. Okay, we'll get back to this question. Let's discuss the topic of kinetic friction in case of rolling motion. So kinetic energy in case of pure rolling. Kinetic energy in case of pure rolling motion. Okay, so suppose a wheel is rolling. Okay, the direction of friction force is in this direction. Okay, there is no external force right now. V omega. Okay. The kinetic energy of this wheel is nothing but rotational kinetic energy plus translational kinetic energy. Rotational kinetic energy plus translational kinetic energy. Okay. So first thing is first, for rotational kinetic energy, you first need to determine the axis of rotation. See, somewhere you take this as the axis of rotation. Okay. In some places you take this as the axis of rotation. I'll explain the difference between those two axes. Okay. But see, whatever axis you take, kinetic energy or rotational kinetic energy is nothing but half moment of inertia through the axis that you have taken into omega square. So it is nothing but half I omega square. Half I omega square. And translational kinetic energy is nothing but what? The half mv square. V is nothing but the translational velocity of the axis of rotation that we have taken. Understood? Okay. Kinetic energy in case of theodomy. Okay. Now see, in some places what they do is they take this as the axis of rotation. This as the axis of rotation. So when this is taken as the axis of rotation, we call this kind of axis as instantaneous axis of rotation. Why is that? Okay, see, instantaneous axis of rotation. Just right. Instantaneous axis of rotation. Instantaneous axis of rotation means the axis that is passing through a point which has zero velocity. The axis, the instantaneous axis, because as this wheel moves forward, okay, this instantaneous axis that passes through this point also moves forward in this direction. Okay, so instantaneous axis is not fixed at a point in space. That's why it is called instantaneous axis. So the instantaneous axis of rotation, okay, is nothing but what? Instantaneous axis of rotation, okay, is the axis passing through a point where the point has zero velocity. Okay, passing through the point where the point has zero velocity. That is nothing but the instantaneous axis of rotation. So in case of pure rolling, the instantaneous axis of rotation would be nothing but the point of contact. Point of contact means this surface, isn't it? And at this surface, okay, I can say V is equals to omega r, because net velocity out here is equals to 0. Okay, so if you take as the axis of rotation, now if you find out the kinetic energy taking this as the axis of rotation, it is nothing but half I omega square. I have to take the moment of inertia about this axis into omega square. Omega will be the same. And why is it the same? I'll explain in another video. Okay, that's the concept of rotational motion, and get that, okay, in some other video. But the moment of inertia I have to take about this axis plus m into v axis square. Now what is the velocity of this instantaneous axis? The velocity of this instantaneous axis is 0, because this point is not moving with respect to space, no, at that instant only. Okay, at that instant, at every instant, the velocity at this point, the point of contact, is 0. So if you take kinetic energy, or if you calculate kinetic energy taking your axis of rotation out here, it will be nothing but half I should be taken about this axis into omega square. Omega about this axis is this one, omega about this axis is also this one. Okay, how, that I'll show you in another video. and if I take this as the axis of rotation, this v axis would be 0. Okay, so let me demonstrate it by an example. So suppose there is a disk, okay, disk of mass m, moving with velocity v. This is a case of pure rolling motion. Okay. So in case of pure rolling motion, I know that v is equals to omega r, fair and fine. Okay. And if it was impure rolling motion, the point or the surface of point of contact would slip, so there would exist some translational kinetic energy. Okay. So kinetic energy. In first case, what I'm trying to do is I'll try to take kinetic energy through this axis of rotation. Okay. So in first case, kinetic energy is nothing but half I. What is the moment of inertia through center? mr square by 2 into omega square. Okay. Plus half mv square. Okay. And we know that v is equals to omega in case of pure rolling. V is equals to omega. So if I do that, okay, substitute it is nothing but half mr square by 2 into omega square plus half m into omega by r. See, if v is equals to omega r, v is equals to omega r, omega can be said as v by r, isn't it? So omega is nothing but v by r. V by r, sorry, v is equals to omega. I'll just directly change the v out here. V is equals to omega r, okay, square. Okay, now if I solve this problem, it is nothing but 1 by 4 m r square omega square plus half m r square omega square. Okay, now if you add these two, it will be nothing but 4 okay, m r square omega square plus 2 m r square omega square, m r square omega square. Okay, so our kinetic energy, total kinetic energy will be nothing but 3m r square omega square divided by 4. Now what happens if I take the axis of rotation to be this one? So let's find out the kinetic energies, the same kinetic energy, by taking the axis of rotation to be this one. Okay, so kinetic energy half how much I. Now the moment of inertia should be taken above this axis. Okay, the moment of inertia is nothing but m r square by 2. I have taken moment of inertia with this axis, and then I apply parallel axis theorem. So m r square by 2 plus m r square. So 3 by 2 m r square. 3 by 2 m r square half I into omega square. And now if you check this one and see, if I take above this axis or axis above the point of contact, there is no translational velocity of the axis. So the total kinetic energy would be 3 by 4 m omega square r square. Now look at the results. Isn't the kinetic energy that I obtained from taking the axis at the center of the wheel and the kinetic energy of the wheel that I have obtained from taking the point of contact, axis at the point of contact, the same thing? Both are the same thing. So it doesn't matter where you take the axis of rotation as long as you remember this formula. Kinetic energy is equals to rotational kinetic energy plus translational kinetic energy. Kinetic energy is equals to rotational kinetic energy plus translational kinetic energy. And the translational kinetic energy is nothing but half into m into velocity of axis square. Okay, till then you are fine. Okay, now let's go back to our problem. Okay, so this was the question, but in these first two cases there was a concept of impure rolling, and suddenly means after a certain while it transitioned to pure rolling. Okay. One more thing. Okay, sir, how do I take the angular momentum? Kinetic energy you said, okay. So what is the angular momentum in case of pure rolling? So write that topic also. Okay, angular momentum in case of pure rolling. Angular momentum in case of pure rolling. Okay. So angular momentum in case of pure rolling. Now in angular momentum in case of pure rolling, suppose a body, okay, or a ball, okay, is rolling out here. Okay. But angular momentum in case of rolling motion, not pure or impure rolling. Let's cut this pure out. Okay. And kinetic energy also, let's cut this pure out here. Okay, that would be valid for all the cases, not only for pure rolling. Okay, so in case of impure rolling, this axis, okay, would slip out here. So it is nothing but half I omega square plus mv axis, whatever is the velocity while sleeping. Okay, so v is nothing but v minus omega in case of pure rolling. Sorry, impure rolling. Okay, so let that be the case. So the case of pure rolling was just to show that both the kinetic energy out here and the kinetic energy out here would obtain the same value. Okay, in whichever method you take or whichever axis you take. You just have to remember kinetic energy is equals to half I omega square, where I is the moment of inertia with the axis of rotation, plus half mv into axis square. And this formula for kinetic energy is valid for both pure rolling and impure rolling. Okay, so let's get back to my problem. What is the angular momentum? See, the angular momentum is nothing but L is equals to m r cross v. Okay, and this velocity is nothing but the velocity of axis of rotation. Velocity of axis of rotation. Okay, whichever axis you are taking, plus I omega, moment of inertia through the axis, moment of inertia through the axis, moment of inertia through the axis. Now in most cases, see, in case of pure rolling, pure rotational motion, there is no velocity out here. In case of pure rotational motion, this velocity term won't be present out here. Okay, but in case of rolling motion, the term of velocity is present. Okay, I have one more problem. See, in most of your cases, you have learned or you have the presumption that angular momentum is defined about an axis. No, angular momentum is a vector quantity, so it is defined about an origin, and the origin is a point in space. So to find out the angular momentum of this body, okay, you first have to define the origin. Let my origin be this one. Okay, or you can define any origin, it doesn't matter. Okay, okay, fair enough. Now as soon as I have defined the origin, okay, m into r into v, what is the value of r? This is the value of r, straight line connecting the axis and origin. Now m into r into v, so this can be said as angular momentum, can be said as m into r into v into angle between v and r, v and sin theta. Sorry, sin theta is the angle between r and v, plus I omega. Okay, I is nothing but the moment of inertia through the axis of rotation. Now if I take this r and sin theta, so if I rewrite this mv into magnitude of r sin theta, if I take this r sin theta, if you observe properly, r sin theta is nothing but this capital R. Okay, I have been saying that in rotational motion for over. So angular momentum is nothing but mvr plus I omega. Understood? Okay, angular momentum of a rolling wheel is nothing but mvr plus I omega. I is nothing but the moment of inertia by this axis, and omega is nothing but the rotational velocity. M is nothing but the mass of the wheel, v is nothing but the velocity, and r is nothing but the radius. Okay, so what happens in case of sleeping? In case of sleeping also let it be. Okay, in case of sleeping, I omega, whatever value is the omega, and plus mvr. Just the difference in case of pure rolling and impure rolling is, in pure rolling v would be equals to omega r. Okay, and in pure rolling v is not equals to omega. Understood? That is the only difference between pure rolling and impure rolling. Okay, so understood the case of angular momentum. Okay, fair and fine. Now let's jump back to the original question that I have told you. Okay, original question from HCB. See this one. This friction force is acting on this one, this friction force, and finally transition to pure rolling. Now there are two methods of doing this. Okay, throughout the internet, whatever solution books you have, okay, they mostly relied on the conservation of angular momentum. That means conservation of angular momentum means, see, one more doubt you might have, sir, how did they apply conservation of angular momentum? There is a torque acting out here. There is a torque acting out here. How is angular momentum conserved? It's not like that. The total angular momentum is conserved. What do I mean is, suppose I take this line, okay? Now my axis of rotation, if I take this as the origin, this as the origin, obviously torque is acting out here. There is a torque out here. I understand there is a force out here. Okay, this is a force out here. My question is, what is the torque due to this force about this origin? This is nothing but R cross F, and the angle between R and F is nothing but how much? 180. So the net torque due to this friction force would be 0. Now you might ask, sir, what about mg force? So if you take this as the origin, mg force is also causing a torque, no? Obviously mg force is causing a torque, but the normal reaction force is counteracting it, no? So the torque caused due mg force is balanced by torque due to normal reaction force. So there is no torque in this direction also, clockwise direction or anti-clockwise direction. So the net torque about any origin kept in a point in space is 0, and therefore you can apply conservation of total angular momentum, not rotational angular momentum of mvr. Okay, the summation of mvr plus I omega would be constant. Okay, understood? This much is clear. Okay, so having said that, the first method of doing this is nothing but by equation. There will be two equations, rotational equation and translational equation. Rotational equation means nothing but torque equation, and translational equation means nothing but force equation. So both the methods are nothing but, in first method, okay, time taken by torque about this axis, okay, instantaneous axis. I'm not considering this as the axis of rotation. For now, let's forget this one. Okay, the first method, time taken by torque, okay, to reduce the angular velocity to 0, okay, is the same time taken by this force mu n to reduce the velocity from v to v1, and by equating the time you will get the value of v1. Similarly out here, time taken by torque to increase the velocity from omega is equals to 0 to omega is equals to omega 2, where omega 2 is equals to v2 is equals to omega 2 into r. Okay, is the same time taken by this friction force to reduce the velocity from v1 to v2, and if you equate the time you get this value. Therefore that is the first method. The second method is, let's take angular momentum, or let's conserve angular momentum to a point in origin. This is the origin, or any other point in this line. Okay, all will have the same effect. Okay, so if this is the origin, the net torque acting on the wheel is equals to 0. So if I apply conservation of momentum, minus m v is nothing but plus mvr. Why is it plus mvr? See, which direction is it rotating? Is it clockwise or anti-clockwise? See, due to this v, draw a straight line. Okay, and somehow encircle the origin. You have to somehow encircle the origin by drawing a rectangle. So this path, this path, this path, this path, and this path. So this is a clockwise kind of angular momentum. Okay, see, but sir, I can do this like this also. This path, this path, this path, this path, this path, this path. Is this a triangle? No. So somehow you have to make a triangle, okay, and encircle the origin. Understood? Okay, so the direction of your motion of the triangle while drawing the rectangle is nothing but the direction of angular velocity. So this v would be clockwise, and this omega is nothing but anti-clockwise. So total angular momentum is nothing but mvr minus I omega. I is nothing but how much? I omega. Omega is nothing but v by r, or v by r, which is nothing but a total angular momentum, because the work done by torque, okay, is 0. Sorry, the torque about this origin is 0. So total angular momentum out here is nothing but mv1 r plus I into 0. The total angular momentum out here is nothing but m v2r plus I omega 2. Here omega 2 is nothing but v by r. Okay, sorry, v2 by r. So if you balance these three means this value is equals to this value is equals to this value, and we'll get the value of v1 and v2. So this is the concept of HC. Okay,
And now I'm going to, so this would be the end of this lecture. Okay, I won't make this lecture too long. So this is going to be the end of this lecture. So after studying it, I'm going to give you a DPP. The least you can do is try to see the questions of the DPP. Okay, and those of you that are going to solve the DPP, that's very good. Okay, if you have any doubts in the DPP, mention in the comment section. And that's all. Okay, take care, bye bye, and prepare well. Okay.